we are off. Step one, to prove the uniqueness of the real numbers is we have to embed the naturals into our sets x and y, and then define an isomorphism between them. So remember, x and y are two sets which satisfy the axioms for real numbers, meaning they are an ordered set, an ordered field with the least upper bound property. So that's what the real numbers are. So we're positing that there are two separate sets that have those qualities, and we're going to show that actually there's only one set, that these two sets will actually be the same set. So to do that, as I said last time, we're basically nailing the two sets down, and step by step, first we're just going to put a nail down at 0, 1, 2, 3, show that they're the same, and then we're going to add the negative numbers to it. Then we're going to insert into that the rational numbers, and then finally the real numbers, to show that there's no possibility of any kind of like twisting or overlap, that they're going to be the exact same set. I'm going to go very slow through this first step because there are a lot of new techniques that we haven't seen before that we need to get used to, and the symbols that we use in this proof take some getting used to. They can be a little confusing if you just glance at them. So I'm going to go very slowly through the first step to get us sort of comfortable with it, and then it'll be easier as we go along. So to do this, the first thing we have to do is embed the natural numbers into x and y. So with each step of this proof, we're really talking about three separate sets. We're going to be talking about the original set, the natural numbers in this case, and then our two sets of ordered fields with the least upper bound property. So the first thing to do is to construct the natural numbers. So as I said last time, one interesting thing about this proof is that in order to do this, we have to gain a deeper understanding of what each one of these sets of numbers is. So the natural numbers, and then the integers, and so on. So for the natural numbers are defined just as an element 0 and a successor function. Call that successor function sigma, which says that for each n in the naturals, sigma n is also in the naturals, okay? That's all there is to that. I just defined the natural numbers entirely. If you remember from when we talked about the Archimedean property, we had to use the well-ordering property of natural numbers in order to prove that. And at that time, I talked about the fact that there is an axiom of induction, and there's the well-ordering principle. And you have to use one to prove the other, but you can sort of do either one. So you can sort of assume that natural numbers are well-ordered and then use that to prove that induction works, or you can assume that induction works and then use that to prove the natural numbers. So for us, I think that we're assuming that induction works, and then we're showing that basically that means the same thing as the existence of natural numbers. So all this says is each number in the natural numbers has a successor. So you start at 0, there's the base 0, and then if you put 0 into the successor function, you get 1. You put 1 into the successor function, you get 2. So 2 is then the successor of 0, and so on. Okay, that's all there is to the natural numbers. So the next thing we have to do is embed these numbers into x and y. And that can be done in a very natural way. We're going to have two, and throughout this again, we're going to have the embedding will be a function that we call e. So there's one to embed them into x and another one to embed them into y. So the first thing is we send, before I wrote this down, we send the least element of n to the 0 elements of x and y. That's the first thing. That is 0x, and 0y. It's really interesting to me, the connection between about what we're doing here, because we know what 0x and 0y are because we got those out of the addition axioms for a field, that 0 is just the additive identity for a field, so that any element of x plus 0 plus this element will equal the original element. So we have one of these elements in each of these fields. Right now they don't mean anything. They could be over at the, if you had a number line, the 0 could be over here on the left side, it could be over here on the right side, or it could be right in the middle. And right now it doesn't really matter. We just know that there's an element that will send every element back to itself. If you add 0 to anything, you'll get back to itself. That's all we know about this. We're going to associate 0 in the natural numbers to this number. Now, again, maybe that's arbitrary. Maybe we could do it with 5, but this is a natural way of doing it, and we'll go from there and see how things work. So we know about 0. So the embedding we're going to do, to embed the natural numbers into x, we're going to embed the successor of n into, so we're going to, the way we embed this is, so this is the embedding of some number, of some natural number into x. So then if we add the multiplicative identity to that number inside x, so we're all inside x here, then that will be how we embed. That number will be associated with the successor to n. Okay? So what we're doing is associating the successor function in the natural numbers to the numbers in x. And so now what we're doing here is the same thing that I just said here, but we're using the other element. There's one other element that we know about from our definitions of the real numbers. From the multiplicative axioms, we know that there is an identity element, which you multiply anything by 1 and you get that number back. We call that 1. Again, right now, as of this moment, we don't have any idea what that number is or how it's related to 0. The one thing that we did learn in our axioms is that 1 is bigger than 0. That's the only thing we know about 1x compared to 0x. What we're doing now is we're going to embed the natural numbers into x and y using 0 and using 1. Until then, now we didn't need to do it that way. We don't know what the sort of organization of x and y are, but now we're going to start tacking them down and say, let's take the natural numbers, start with 0, add 1 to 0, we'll call that 1, add another one, we'll call that 2, and so on. So now we're embedding the natural numbers into x in this way. And then you can also say that this equals the successor function of e to the x. So what we have here, this last step is sigma x equals this 2. So what we've done, we have the embedding that's in x, the embedding of the natural numbers into x. This is an element of the naturals. This sends this into x. What we do is we take another number, we take the previous number of the naturals, add 1 to it in x, and that will equal this. In addition to that, we have the successor function in x, which we can now define in the same way. So if we have a natural number in x, we take the successor function in x of that number, and it means the same thing. You take this number and add 1 to it. So we're associating the successor function in the natural numbers to the successor function in x, okay? And then we do the same thing for y. Equals e to the y, and then plus in y, 1 in y equals the successor function in y of e to the y n, okay? Now these are unique mappings of the n's into x and y because zeros, the two zeros are unique. We know that from the axioms. The ones are unique. We know that from the axioms. And furthermore, from there, each one of these numbers is unique because the successor function of n is unique in the natural numbers, and adding 1 to a number in x is a unique number. So we've just associated unique numbers with unique numbers. So just to say one more thing here, we can also see that we can associate addition and multiplication in the naturals with addition and multiplication in x and y, again in a natural way. So just to write it down, if we have that e to the m plus e to the successor of n, that equals e to the m plus e to the n plus 1, and e to the m times e to the successor of n equals e to the m times e to the n plus e to the m. So these aren't axioms, they're just obvious from what we just did above. So what we're saying here is simply, the first one says that e to the successor function of m equals e to the n plus 1, right? So then if we're adding e to the m to both of them, these two are equal. So this equals this. The second one is just the distributive property, because now if this equals this, then we have e to the m times e to the n plus 1, which is just e to the m times e to the n plus e to the m one more time. Okay, and notice the reason I don't have an x and a y here is because this is just generic. I'm talking about both of them. I could do them separate, but the point is this property comes from each one of these. So they're not really I'm not really providing you any new information here. They come from this. Okay. Now, so that was the embedding. Next, we have to define the isomorphism. So now we're defining an isomorphism from the natural numbers in x to the natural numbers in y, and vice versa. So I'll just define that and then we'll look at it. So all this says is very simple. I could have written this more simply. I could have just said e to the n to the e equals e. So that's all there is to it. This is super obvious. We're just saying that whatever the embedding of n is in x equals the embedding of n in y. That's the isomorphism. Or I should say that's the mapping. Now we need to prove that this mapping is an isomorphism. And one thing to point out here, which we'll be seeing frequently, so we're actually defining 4 separate maps from numbers in x to numbers in y. So I'm specifying which one we're talking about as well. So this isomorphism, this map just is for the naturals to the naturals. So then after that, there will be another one with phi z, phi q, and finally phi r. So what we need to show is that this is an isomorphism using the 3 properties which will define an isomorphism between fields. We need to show that they're plus, multiplication, and ordering. So, okay, so now we're going to prove our first isomorphism. What the isomorphism says is that what we did with the embedding was we just put the natural numbers into x and into y. Now we have to show that in fact those 2 embeddings are isomorphic, which means that they have the same structure, which means that if you add numbers in x, if you add natural numbers in x, you're going to end up with the same natural number in y. So to prove an isomorphism, we have to show that n is a bijection that satisfies 3 things. 1, that n of u plus v equals phi of u plus phi of v. So again, just to interpret this one more time. So this is our mapping. U and v are elements of x. So u plus v, this is the addition in x. So we're adding them in x and then mapping them to a number in y. Here, we're mapping u to y and mapping v to y, and then we're adding them together using the definition of addition in y. So I think I showed this in the last video. So basically, we're making a what we're showing is that it doesn't matter which direction you go with this map. You start here with u and v, you add u and v, and then you map u and v, and you end up here. Or you can take u and v first and then add them together after you're up in y. So u plus. And the point is that if you start here, no matter which direction you go, if you map to y first, then add, or you add first and then map to y, you'll end up with the same number in y. Number 2, so u times in x v equals phi of u times phi of v. And I'm using x here. Obviously, uv means the same thing. I'm just using x to make it clear that it's kind of, to me, it's more clear that it's parallel to multiplication, to addition. And 3, that if u is less than v in x, that implies that phi of u is less than phi of v in y. Okay. Bijection. So we have to show for a bijection that the map is well defined and that it's onto and one-to-one. So here, just to see that it's well defined, we can see that for every x in x, there's at most one n, such that x equals e to the n, and embedded in x. And that's because given x plus 1 is unique, and each n equals, right, so each n you get by just repeatedly applying the successor function to each one, and then you'll get each n uniquely. And the successor of 0 equals 0 plus 1. So that means that each one of these has to be unique. So it's well defined because whatever x is, you're only going to get 1 in y. As for one-to-one and onto, that's just by the construction of the isomorphism, because the isomorphism is that, so it has to be onto, because clearly you start at 0 and each one is going to go to one of them from in y. And it's one-to-one again because, as we just said, it's unique, so there's only going to be one for each successor. There's just going to be one. So that's pretty straightforward. Okay, so before I prove the three criterions, addition, multiplication, and ordering, there's a lemma that we're going to use. I'm just going to sort of take out this one fact that we're going to use over and over. If we let m equal, and the embedding of a for a in n, then so m is an element of x, and so this is the successor function in x, and this is the successor function in y, right? Because phi of m is in y. So what this lemma is doing is saying that you can either take the successor first and then apply phi, or apply phi and then take the successor. So it's almost like another aspect of the isomorphism that you can do. You can either do it in x or you can do it in y, and you'll end up with the same thing. So I'm just going to prove that because we're going to use this repeatedly in the proofs of the three. So now a lot of these proofs, once we get to them, they're just algebra. The proofs themselves are very straightforward and something that I find fun to do, just applying the different axioms one step at a time. So we start with phi of the successor of m, that equals. So this is just the definition of sigma in x. This is the definition of m. This is the definition of the embedding of x. Remember, if you take this, then it's the same as just taking the a and adding 1 in x to it. This is the definition of phi. We have it here. That you have something embedded in x, you take phi, and you get the same embedding in y. That's all we did here. So we have the embedding in x of sigma alpha, and then that equals the embedding in y. This is the definition of the embedding into y. This is the definition of sigma. Now, again, this is again the definition of phi. Phi of an embedding equals the embedding in y. And finally, this is again just the definition of m. So that's it. We started here with phi n of sigma x of m, and we ended up with sigma of phi of m. Okay. Now I want to point something out. Here's something else that we're going to do over and over, and this is actually one of those techniques that is fundamental to proving things in math. When you're trying to prove something new, you take it back to something that you already know. Do the manipulation in the realm that you're comfortable with, and then you take it back to the other one. So that's what we did here. We started with what we're trying to prove. And then what we did was step by step, we took it back to the naturals and just the embeddings of the naturals into x and y. Then we did we switched it back here in the embeddings, and then we went back the other direction. So then this is the definition of sigma in y, and then change it back to the phi's, and we ended up there. So we basically went down and then over in the embeddings and then back up after we've done the work down below. So this is a very common way. We'll do this over and over. You go down, over, and then back in order to get the equality across. Okay. So now we just have to prove the addition, multiplication, and ordering. Okay, addition. Let m be an element of x. So we're going to prove additivity for phi of n by induction on n. Okay. So what this means is, why do we have these? We have to show that addition works for any two numbers in the natural numbers. So we're just taking an m arbitrarily, and we're showing that phi will work for every n added to m. So we're going to do m plus 0, m plus 1, m plus 2, and so on. That's the induction that we have to do. So the first step, let n equal 0. So we have phi of n of m plus 0. This is all in x, so m plus 0 in x equals, that's just the additive identity in x. And then from that, so this is in y, so we know that we can add 0 in y and get the same thing. That's the additive identity in y. And then we can change this. We know that 0 in x is sent to 0 in y. So we have m plus 0 in x equals the phi of m plus the phi of 0 in y. So that's the 0 step. Now the induction step. So for each m in x, assume additivity is true for n of x, then we'll show it's true for the successor of n. Okay, so if it's true of n, we're going to assume it's true of n, and we'll prove that if it's true of n, then it's also true of its successor. By doing that, start at 0, and then you've done them all. In other words, this is n plus 1, right? So again, here's just a big block of applications of the various axioms. So we start with phi of n. So the definition of that is m plus n plus 1. Right, that's the definition of sigma equals. Now we're just going to do associative, m plus n plus 1 equals. Now this is just the definition of sigma in y. I'm sorry, the definition of sigma in x. This is the definition of sigma in x. So we have sigma of m plus n. Now using our lemma, phi of sigma, it equals sigma of phi. So we're just going to flip this out. I'm afraid we're going to run out of room here. And then we have sigma of y. Now we have, so what did I do here? I took phi of m plus n equals 5m plus m phi of n. And you're wondering, but isn't this what we're supposed to prove? That's how induction works. We're assuming that this is already true for n. What we need to prove is that it's true for the successor of n. So what we did is we got down here to this we're assuming is true, and now we're adding the successor function to it. So next page. Okay, so let me just write that down again. We were on, now the definition of sigma is y this plus 1. So we have, right, that's the definition of sigma. Oh no, wait, I'm sorry, not, the definition of sigma is what's inside plus 1. So now we can just use the associative property here to rearrange the parentheses. And now we can use the definition of sigma in y. Now we use our lemma again to move the sigma inside. And we have the sigma plus phi of the sigma of n. And that was what we wanted to show, because what we wanted, so what we've shown is starting from phi of m plus sigma of n, that equals phi of m plus phi of sigma n. So therefore, I understand this can look a little bit cryptic, but all we've done is we've shown the first step of phi, the addition, which is that if you add something in x and then take the phi and then phi to map it over to y, you're going to end up in the same place as if you take phi of each element and then add them in y. This is the first step of the isomorphism. And why are we talking about sigma? That's because we're doing the induction step. We assumed it was true for m plus n. We're showing that it's also true for m plus sigma n. So now we showed that it was true of 0, and we've shown that if it's true of any element of n, then it's true of the next element of n. That means that it's true of all of them because it's true of 0. So it's those two things put together. It's the induction step, and then we're showing the addition property for the isomorphism. So that's it for addition. So we just have two more things to do: multiplication and ordering. So multiplication should be very similar to what we already did. So we're going to do it by induction again. Let m be an element of the naturals in x. So we're going to use induction to show that m times n in x, and then mapping it to y is the same as equals mapping it first and then multiplying it in y. So first step, let n equal 0 in x. So this is m times 0 in x, which we know from the axioms is 0. So that equals, so this is just, we're still in x. We're just, this is just the 0 property of multiplication in x. So now from here we can multiply this in y, right? So this is 0. This is 0 in y. So anything times 0 in y is 0. So these two are equal. So finally, and 0 in y is mapped from 0 in x. So that's what we wanted to prove, that m times 0 in x equals m times 0 in y. That's the initial step. So we just showed that multiplicativity is true for when n equals 0 for all elements m in n. Now the induction step. So again, assume it's true for n and all. Okay, so we're taking for any arbitrary element m in x, we're assuming that the multiplication of the isomorphism works for n in x. So now we're going to show that if it works for n, it's going to work for the successor to n. So we need to show that it's true for n for the successor to n. In other words, n plus 1 in x. Okay, so again, just a series of applications of our various axioms. So we start with n of m times the successor of n. So remember, we're assuming it's true for n. So what we're doing is now we have to show that it's going to be true for the successor to n. In other words, that this equals phi of m times phi of the successor to n. That's what we're trying to get to. So definition of sigma. So this is just m times an addition. So x has the distributive property, so we can just distribute this. So we have m times n plus m times 1. Now anything times 1 is just m, so we have m times 1, need one more parenthesis, plus m. Now we've already verified that that phi has the additive property, so we can apply what we just used to this to say that n of m times n plus in y, okay, this is the additive property of phi, which we just showed. But now we have, by assumption, we already know that multiplication works for m and n. That's our assumption step. So now we have put parentheses around these. So now it gets interesting, because now what we're going to do is reintroduce 1 back into this equation so we can get to the successor function. So anything in y times 1 is the same. So we can rewrite this right, because m times 1 equals m. So we haven't done anything there. So now we can use the distributive property in reverse. We're basically factoring out the m's, right? So we have n times m, and now everything we're doing is in y, times n plus, and now this is just the definition of sigma. And finally, what do we do with this? We use our lemma, and we're there, right? Sigma of phi is the same as phi of sigma, and that's it. We started with phi of m times sigma of n, and we ended with phi of m times phi of sigma times n. That's what we wanted. Okay, that's multiplication. One more step. One more thing to prove. Ordering. Okay, so this is a little stranger than the last two. Let m and n be elements of n in x. If m is less than n, then there exists a non-zero natural number c in n such that m plus c equals n, right? What this means is that if m is less than n, we're talking about natural numbers, so it has to be, the difference has to be a natural number. So if we let c, so there's some natural number c such that m plus that number equals n. And we know since m is less than n, not equal, that, so c does not equal 0. So it must be that c is greater than 0. So c is not 0. This means that since we've shown that phi of n is 1 to 1, then phi of c cannot be 0, right? Because there's only one element in the natural numbers in x that maps to 0 in y. So this has to be something other than 0. So that means also that n of c has to be greater than in y, 0y. So with this in mind, if we start with phi of m, we can add 0 to that, and that is less than phi of m plus phi of c. That's only because we know that c is bigger than 0. And this equals, we know the additive property of phi, so phi of n, we can combine these, m plus c in x, right? This equals this because of the additive property. And we started by saying that m plus c equals n. So this equals phi of n, which means that phi of m is less than phi of n. So we just showed what we needed to show. We started with m is less than n, and we ended up with phi of m is less than phi of n, which was what we have to prove. Just write that down again. Phi of, or oops, I'm sorry. The third step of the isomorphism is that m less than n implies that phi of m is less than phi of n. Okay, so we have shown the three things that we needed to show to prove that phi n is an isomorphism. It's additive, multiplicative, and the ordering is preserved. Or another way of saying it, I think, is that addition is preserved, multiplication is preserved, and ordering is preserved. That means that phi of n is an isomorphism. And so what that means is that for any two sets, x and y, which satisfy the real number properties, meaning that they're an ordered field with the least upper bound property, for any two sets that satisfy those properties, we can embed the natural numbers into each of them and find an isomorphism between them. So what that means is that at least as far as the natural numbers are concerned, if you have two sets that are ordered fields with the least upper bound property, at least as far as natural numbers, those two sets are isomorphic. So the question now is there still wiggle room in there? Maybe the integers are different, or maybe the rational numbers, or maybe you can use the least upper bound property in a different way. So we've shown that at least the natural numbers are, there's only one set of natural numbers. They're going to be in x and y in the same way. So now we have to just go through the rest of them and show with integers, rational numbers, and real numbers that that's also true.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.